Hi, this is Mr. Mac. This is the third video dealing with limits, and I think maybe we could call this one evaluating or how limits behave. So I'd like to start off with some things that probably should be obvious, but probably need to be stated. If you have the limit of, as x approaches a, of two functions, f of x plus the limit as x approaches a of another function g of x, that would be the same as the limit as x approaches a of f of x plus g of x. In other words, if you are finding the limit of two different functions at a particular value a, and then adding those limits together, you'll get the same answer that you would get if you added the functions together and then took the limit as x approaches a. I know, I think at least, it seems pretty obvious. Now, it's also true that if you subtract the limits of two functions as x approaches a, that you would get the limit, if you subtracted the functions first and then take the limit, you'll get the same value. Now we can also use times here, and we can use division here, as long as the limit of the bottom function, this one, is not equal to 0. So you can move functions in and out of a plus sign, minus sign, times sign, or division sign with the limit notation. Now, it's also true that if you're taking the limit as x approaches a of some constant times a function, that would be the same thing as the limit as x approaches a of the function multiplied by the constant. If you take the limit as x approaches a of some constant, you're going to get the constant. You know, as x approaches 7, what is 2? Well, it's still 2. And if you take the limit as x approaches a of x, you're going to get a. I mean, these things have always seemed to me to be pretty obvious, but it is good to state them. Now, if you're taking the limit as x approaches a of x to the b, you're going to get a to the b. Now realize that b as an exponent doesn't have to be an integer. It could be a fraction or something like this. So it's a subset of this, the limit as x approaches a of the nth root of x is going to be the nth root of a. Just let b be 1 over n in this statement here, and you get that statement. Now that also means, though, that the limit as x approaches a of the nth root of f of x is going to be the same thing as the nth root of the limit as x approaches a of f of x. Now, we get to the point where we have a couple of theorems, statements of theorems. I'm probably not going to be proving these to you, but they turn out to be very useful in actually evaluating or determining what the limits in particular positions are. Okay, now first of all, if f of x is a polynomial or a rational function defined at a, then the limit as x approaches a of f of x is equal to f of a. So if you have a polynomial function or a rational function that doesn't have an asymptote at a, then you can just put a into that function and the limit of the function is equal to that value. That happens because polynomials and rational functions on their domain are continuous. And you would call, okay, and this brings up a computational technique for computing or evaluating limits, and we call it direct substitution. In other words, if you want to know the limit of a function as x approaches some value a, try putting a in, see if it gives you a value. If it does, and the function is continuous there, then that's the limit. Now, the next thing that we have is if you have two functions, if f of x is equal to g of x, for all x not equal to, let's see, let's do a better job on the for all. For all x not equal, I don't know why I'm having such trouble today, not equal to a, and if we know the limit as x approaches a of f of x equals L, then it must be true that the limit as x approaches a of g of x equals L. Now, this situation occurs when one of these functions has a removable discontinuity. Let's, for example, let f of x be equal to x plus 3. Then, and we'll let g of x be equal to x squared minus 9 over x minus 3. Now, if you think about this for a minute, g of x is really x plus 3 times x minus 3 over x minus 3. Now, if we were to cancel the x minus 3's in g of x, we would get x plus 3 comma x is not equal to 3, because remember, when you cancel a factor, a variable factor in the numerator and denominator, you have to exclude the values that make that factor 0 from the domain. So g of x is really f of x with 3 excluded from the domain. So if we were to ask, what is the limit as x approaches 3 of g of x, if we try direct substitution, we would get 3 squared minus 9 over 3 minus 3, which is 0 over 0. Now, this designates an indeterminate form or a removable discontinuity. Now, what we're saying is we know the limit as x approaches 3 of f of x is equal to 6. And f of x and g of x behave exactly the same every place except at 3. Since at 3, this is a removable discontinuity, we can just go ahead and remove it in this particular case. And we get the limit as x approaches 3 of g of x will also be 6. Now, this method of evaluating limits has some ramifications and some computational consequences that you'll be seeing very shortly. This one becomes very important because what we end up with is when we're trying to take the derivative, we make the definition that it's a limit, and we do get a removable discontinuity, and we remove it. And this is the basic reason why that will be allowed to be done. So you might call this technique of evaluating limits removing removable discontinuities. Now we have another fundamental computational concept here, and this one's called the squeeze theorem, or the sandwich theorem. So let's start out. If you have three functions, f of x, g of x, and h of x. Now, and if on some interval b to, open interval b to c containing a, in other words, a is an element of in the open interval from b to c, and we know that f of x is less than or equal to g of x is less than or equal to h of x on that open interval containing a, and if we know the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals L, in other words, it's equal to some limit, then, here we go, then we know that the limit as x approaches a of g of x also has to be L. Now, I'd like to show you this with a picture. So let's take a look at a picture of what's going on here. We know that f of x is less than, here, let's put a right here. F of x is less than g of x for all values except perhaps at a. And we know that h of x is more than, let's call this f of x, and h of x is more than all values of f of x on this interval. And we have g of x doing something in here. But since the limit of f of x is L at a, and the limit of h of x is L at a, then g of x is squeezed in so that its limit also has to be L at a. We call this the squeeze theorem. If you can get the two functions, the top function and the bottom function, to squeeze in on a particular value, and you know that g of x has to be between those functions at these values, then g's limit has to be the same. Now, I think maybe I'm going to go ahead and stop here, and perhaps I'll do another video where we actually do some computations of limits. But this is basically, these three videos are basically the concepts that we have behind limits. Now, there are other techniques to evaluating limits than the ones that I've mentioned here, but this is kind of fundamental or a start for it. So, we're done.